No, no, I have. Thanks.
Okay, welcome back. Our second speaker for today's morning session is Soham Ray from IIT Roorkee, who will be talking about the complexity of interfacial SLIM. Okay.
Yeah. Hello, everyone. So I'm Soham, and I'm from IIT Roorkee, and the departments that I work on are earthquake engineering and School of Data Science and Artificial Intelligence. So, little bit about IIT Roorkee, and as you might be aware, it's a remarkable place for both engineering and sciences, given there are a number of departments focused towards earth science, mechanics based studies, and particularly earthquake engineering department has a culmination of 3 sub-disciplines with very strong focus in structural seismology and soil dynamics, completing all the aspects of the earthquake. Yeah. So, and I thank organizers, in particular Debayan and others, for giving me this opportunity to talk about this work. And this is mainly about the interfacial slip and how slip conditions or the interfacial conditions dictate sometimes a faster movement, sometimes a slower one. And yesterday we did see Kaushik's talk on how the bulk and interface combine together to give a fantastic range of motions phenomena. So I tweaked my talk little bit after Kaushik's talk yesterday. So I focus more on the interfacial properties rather on the bulk ones, and we see that there are various realization that simple laboratory based frictional and strength formulation allows us to do so. So bit of a motivation first, and that you are aware that the subduction zones and these are can host remarkably host of lots of motions. I mean, so from very slow and locked at some portion, still pushing by, and all of a sudden there is over a very short time scale there is a rapid motion, and that cascades like lots of other processes within the earth. There is slight error in this, so I'm not going to that detail, but yeah, so let me replay this one. So you see the scale goes like years and years for like 100, 200, and then suddenly within a seconds you get an instability which we call, and that kickstarts an earthquake that propagates through the medium, and that creates like tsunami and other things. And on the left, again, maybe an appropriate citation is required, but it's pretty standard in our community that all of these motions have a strong bearing on the interfacial properties and how they look like. For example, whether there are frictionally stable regions, there are asperities which are considered as frictionally strong, and how they are distributed, their sizes. So there are lots of controls, and in terms of physical processes, there are like fluid flows within that, there are a diffusion of pressure that changes the strength conditions, and the range of physical processes are enormous. But in this talk, I will touch only the bare bones modeling choices and its consequences, and simple modeling choices, and that we'll see. So maybe a little bit more pictures. So what happens, we also get a surface indications. For example, the figure in the between and maybe in the left. So let me try to run it. So you can, so they have surface indicators. For example, after an earthquake, you can see there is a split apart. So let me try if it runs. Yeah. You see, so this is on the surface. So whatever happens like 20 kilometers deep, you not only get in waves, but you can get an actual motion. And again, these are taken from various standard sources in our community, and so yeah. And what happens at the base are like there are lots of motions that happen which are recorded on the top, and these circles indicate the depth and the magnitude of such sliding motions. Point is, whatever happens, there is some relative sliding happens within an interface, which is hosted within an elastic medium of rock. So point is, rocks can store energies, and they can release energy, and when they release energy, and what we feel are the seismological elastic waves, and this is the part of seismological studies, and you know these are standard, our inertia, then body force, then the divergence of the stress. You can use simple constitutive elastic relation to and put it back here, and you get two kinds, at least transverse longitudinal waves. But the focus of this talk is not to simulate elastodynamics through the earth, is just to make the point that this is the source of all the waves. And this source in seismology, when viewed from a little far, just like we view a coffee mug, a warm coffee, it has a molecular motions which average out to form a macroscopic temperature. In same way, there are lots of phenomena happens within the earth, which in the fault there are sliding, there are slip, there is a rapid slip, there is slow slip. All those are while you model elastodynamics through the earth, then we club in one body force term, and they have their equivalent representative. So this talk is not about how waves propagate through that. This talk is mainly to concern the sources of such seismic waves within the earth. Okay, so again, the bottom line is there are so there are a substantial sliding motion, slip motion goes on, which we want to understand. And so this is, they can have an openings, mainly these two modes we mainly talk about, shearing. So let's march forward. So simply speaking, although fault zones or any interfacial geological condition, they have damage zones, but we for now neglect these damage zones. Reason because there is a slip localization phenomena, and we can consider that a fault, geological fault, or a landslide kind of a setting as just a slip on a mathematical plane. By slip, I mean there is a relative displacement between two surfaces which slide past each other, and this is the definition of the slip, that's a relative displacement. And the damage zones, although they are wide, the actual slip zones are very, very thin, and so this idealization is not very far from realistic conditions. And also realize that a part of the fault or part of the interface can be slipping, and the other part can remain relatively still and not slipping at all. So you see that you can think it in terms of the thermodynamics, that one part is fluidy, other part is little bit frozen, something like that. So yeah, in that sense. So slip we defined, slip is defined as we are aware. Then there are tractions that are resolved at the interface, and that traction is whatever the external tectonic loading conditions or some loading that we saw yesterday. So in absence of any slip, so there is no slip or maybe just uniform rigid, so we just get traction equal to the any external or traction realized at the surface, any external traction applied. But if there is a slipping, slip happens, then we get a change in the traction from external to some other quantity which is slip dependent. So this is purely due to deformation, and we can model this elastically. So there is a relation between the traction at the base or between the interface and the slip that happens. Okay, and the closure condition that when a fault slips. So one closure condition we can put in terms of simply that the stress that is at the interface is equal to the strength of the interface. In this case, maybe it's purely frictional. Okay. So going ahead, so just to motivate this further, in its right. There is we can discuss it maybe for an hour. The phenomena and the dynamical system that permits localization to solutions which are mimics just a planar interface. So those are also observed that there are damage zones, but actual slip zones from the core studies, they seem very thin. So this situation, like damage zone not considering, it's not remarkably oversimplification. It has quite a bit in it. So yeah, talking about faults, in what way? So it could be anything. For example, there's a half space just about a rigid. So this all part is rigid, and this is deformable half space. And if you follow the literature a little bit, so there are ways in which you can actually express the stress at the base as whatever stress we apply, and a slip dependent, in fact gradient of slip dependent, I mean Hilbert, this is a little bit singular as we saw yesterday as well. So it's a Hilbert transform of the slip gradient, and you see this is a singular integral. And because it's integrated throughout, you see there is a non-locality involved here. So slip at one point affect the stress at the other point, or stress at one point affect the slip. So it's like that. So keeping this little bit aside, although it's a very nice relation, but we may be preferring simpler relations. For example, for this kind of a thin slab or a slender object, so maybe it's a landslide or a glacier mass, the relation is remarkably simple, just a Laplacian of the slip. So I forget to write the relation here, but I think it will be coming soon. Yeah, yes. So the same stress at the base, whatever stress we apply in the form of either loading or through velocity is equal to external plus any elasticity driven, and we can do elasticity driven stress changes, and we can do a simple force balance, and we can see that this is placed. Force balance, while we're doing, we can consider it some depth averaged form, so I'm not going in that detail. So point is, we have elasticity, interfacial elasticity is different. I mean the formulation looks different, and these are just two end members. One is thin, one is infinitely thick, like that. Now let's come little bit on the strength part, and you see this is the strength of the interface that can, I mean this is the simplest possible strength that that there is a slip happening, and all we found that the when stress is equal to strength, the strength is just one number, residual tau r, and there may be a background, so tau x is tau b, there is a background stress, and at the interface we get tau r, and we can solve this simple relation to find a slip distribution like that, where at plus L and minus L slip goes to 0. So this is the scenario for the strength, which is just this dashed this red line, not these two. So you see this is like a singular crack, there is a stress drop here. These are the external stresses, which is tau b in this case, and you find a slip distribution, and the stress looks like, so it's a crack. It looks like a crack, but what about the propagation condition? How we know that this is a crack and it will going to propagate? So we need something else. We'll come to that. Just to complete the picture, so when we have other strength formulation, that is strength is just slip dependent, like EDA 1977, Rice, and those model Dugdale Barenblatt types. So you see when we have going all the way weakening, then we can have this kind of So singularity is taken care of by reformulating a cohesive zone kind of a strength formulation, and we do not have infinite but a finite but tau. So these are tau p. So we can have tau residual and tau external outward, and when, so this is the model 3 where we drop and then settles to a one particular place. So these are slip dependent constituent formulation, and they are crack, and you see this is different profile here and profile here, so there is no stress singularity here anyway. So again, so what's the propagation condition, and that condition we can simply formulate in terms of let's do this for just problem number 1. So we can solve this part. We can compute energy density because we know what are the stresses inside this. Once we know the strength density, we can compute the what we call total energy, internal energy. So point is the bulk can send energy if there is a crack available, and when the crack will grow, that is the, so that energy is expended to increase the surface length or surface area. So that calculation we can do. So it's just energy which is expended at the whole crack of length L. So we get this formula, and suppose we know what G sub C is, or G sub C, that is the fracture energy here. So we can get a critical length after which a crack can propagate. In this way, formulated through the one parameter G sub C. So there are other ways to go for, so I just chose the simplest possible relation, which is not often chosen, and these are the models that people generally go for, and we'll come back to this part. Although it's just a slip dependent strength, but it has a it captures all the bare bones or the essentials of crack propagating. So once we have a sophisticated strength, we will have the same or more lab-based strength formulation. We'll get a different LC, but point is there exists a critical length for a crack growth. So that's. Let's move to experiments little bit. So in lab experiments on just sliding blocks, it has been seen, I mean, on range of rock samples in range of and all labs performing these experiments, that the frictional strength between the rock samples are sliding rate dependent. And you see, for any sample, for example, there is a decay in the strength for many samples. So this is like a weakening with respect to sliding rate. And there is another form of weakening which happens around seismic speeds, that there is a further weakening. So this is, so we are not going in this detail. Let's having a low sliding rate formulation and see, this is called as velocity weakening. So your strength depends on the maybe the pore pressure, or you can just ignore it for a while, and effective normal stress, then friction coefficient, and friction coefficient indeed has a sliding rate dependence, so it decreases. Story is not over here. This is a little bit of an ill-posed problem. We can discuss it length if time permits at the end of the talk, and how this ill-posedness is removed by just having two effects. So indeed, many rock samples do show that there is a velocity weakening, that your strength, your frictional strength weakens with sliding rate, but they do so not directly but by two effects. First, we call this a direct effect, that is a increase in the strength, then a subsequent evolution effect, that is a decrease of the strength. Okay. You can plot the same thing with respect to slip. So suppose the two rocks that we initially were sliding at one velocity and later little bit higher velocity. So first the rock samples were sliding at this velocity, and there we multiply by factor v and sliding it at a higher velocity. The moment there is increase in the loading rate of the or the sliding rate, we get a sudden jump in the friction value, and so there was a friction value for this particular sliding rate. We get a sudden jump for due to this increase in the sliding rate, and that and it doesn't stay there, and ball rolls to a different steady state. Just note that this is a velocity v corresponding to this sliding rate, and this is FSS or steady state friction corresponding to this sliding rate v over small v. And important to note that these two are not identical, they are different, and this evolution needs an equation of its own. So there is a direct effect that takes care and an evolution effect, and that this inclusion of a delay term or memory term actually regularizes an otherwise ill-posed problem, which we'll discuss some other time maybe. So please feel free to interrupt me because there are tons of details around these places. So steady state friction theta looks like this, okay, and B and A are the coefficient by which the eventual weakening happens, and A is the direct effect which is strengthening happens. So yeah, so this is not very different from what we just saw with the slip weakening form. So it's a slip weakening. Here also there are slip weakening, but it happens through a different mechanism, and they have a bearing in what we understand about the earthquakes and how they start, how they nucleate. So yeah. So going further, I think this pictures explains pretty much everything, that if you change the sliding rate, your rock samples show these are experiments, real experiments, so no words required. So this is what we see, people see, that's what we see. So going into the details, so if the direct effect is subdominant compared to the eventual weakening, these are the scenarios which is referred to as rate weakening region, and they are the ones which are responsible for rapid sliding. If the interface has this property, they are the ones that provokes earthquake. The strengthening regions are the one where stable sliding happens, but the story is more complicated than this. So just having a rate weakening region does not guarantee that you are going to get an earthquake. As you see that there should be an energetic condition, your length of the crack should be large enough so that you can grow the crack eventually. So how these translate to this lab-based formulation, lab-based friction. So bottom line again is friction is just not one number. It has a sliding rate dependence and a state dependence on that. Okay. So here we start to couple or start to understand. We take a simple model. You can take an earthquake, you can take a landslide type of a case, a simple relation between the stress, traction at the base and the slip. So that's elasticity. You incorporate a closer condition that this is equal to the strength, and the strength is given by rate state dependent. So when you rearrange the terms, you get a differential equation that looks like a partial differential equation that looks like this. Okay, so that's coupling. So let's see, we just simulate it, and we can have a various realization. So before going to that, so what we say that we coupled elasticity, which can be earthquake types, landslide types, with the strength, and we formed a PDE. And these are the length scale that comes from the coupling of elasticity and the frictional thing. So we'll come to that. So the acceleration looks like that, and we want to know that under what condition the sliding rate can become faster, slower, or what that. So what we do, we go for simple dispersion relation, or you can call it a dispersion relation, stability analysis, scaling analysis, that goes by simple name. But what I feel, we just substitute the corresponding eigenvalue of this operator, making the whole extended body shrink to just a spring block, and that is the dominant, and this is the dominant, this is the one wavelength. Okay. So when we do this, we find that one of the modes could be written just like that. And you can see here that the sliding rate with respect to time evolves through this situation, and a positive of this bracket ensures that it grows with time always. So that gives you an indication that wavelength of perturbations that you do, if it crosses this limit 2 pi times some length scale, that length scale is coming from friction and elasticity and this friction, then we can get our slip rate to grow faster and faster with respect to time. So this is one condition. So we need rate weakening patch, as well as we need the wavelength of perturbation and or the length of the rate weakening patch long enough to permit any kind of growth in the sliding rate. Okay. So going forward, so again, simple model that we had, we find that we need a rate weakening patch, and when wavelength of perturbation exceeds this elastofrictional scale, then we can get slip to accelerate, and they accelerate via this v square over, by v square. So it scales with a square of the sliding rate. That indicates that this problem, so this is simple elasticity, this is lab based strength formulation, and this permits an instability in finite time, and this finite time instability is the reason that we get an earthquake. So interfacial may be sliding slowly initially, then at some stage it started growing faster and faster, and that instability is reached within a finite time, and we get a massive sliding rate that provokes the inertia of the top layer, and which permits the transfer of the waves. Anyway, so we can use this, and let's try to see what simulation suggests. So you see, I give a loading rate, there is a frictional value here, A over B, and given a loading rate, you see there is a unbounded growth of sliding rate. So this is, and it happens over a patch length. So we need a length. So what the singularity indicates, this singularity, see the scale, indicates that the physics is changing in the problem. So now we need to incorporate some other physics, but what it tells, it resolves all the conditions that permits a slip rate to grow. So you need a large enough sliding surface which has a rate weakening properties. If this is large enough, and that is quantified by the elastofrictional scale, then you get a singularity in the sliding rate, and that singularity is an indicator that your fault is now ready to dynamically propagate slip and become the source of seismic waves. Okay. So I'll come to this heterogeneity part in a second, but yeah. So resume so far, what we get? So we get that frictional strength is rate and history dependent. Elasticity and friction together gives a length scale for the problem called as elastofrictional length scale, and for this thing, the elastofrictional length looks like this, and for another end member where there's a more earthquake-like, elastofrictional length scale looks like that, and d sub c is the length which is coming from the decay of the friction towards a renewed steady state. So friction law is essentially giving this length, and because we have elastic model, so these things are coming in anyway. And what we saw that a minimum crack length or the minimum patch length is required to nucleate an unstable acceleration, which then becomes a source of seismic waves. And we also need rate weakening region, and that length slightly differs for different elastic configuration, but that is just details anyway. So story is that slip rate initially, if you give any perturbation, it localizes, then hits the patch. If you give a perturbation for a longer size, then it hits a patch and then grows. And if then inertia of the medium kicks in, and then that prevents the singularity to happen. But if you suppress the inertia or any radiation damping kind of a setup, you'll get an unbounded slip rate. So why this is useful? It's useful because it resolves all the condition for instability to happen. So let's go further. I mean, this is just another detail, just to highlight the importance, the why we see. So even if you give a perturbation over a very shrunken region, a high velocity in a very low support, very short support length, it expands. Instead, it contracts if you give it a on a larger support length till it hits the this length, and then only your sliding rate grows anyway. So model that we had so far is very simple. One elasticity and friction, they give one length to the problem. But this might be an oversimplification because earth crust, subduction zones, they are, data suggests that they are frictionally very heterogeneous. So are there consequences of including a heterogeneity? By including heterogeneity in frictional parameters like those jump, rate, direct effect and then evolution effect parameters, they can be different at different points on the fault. So is it unnecessary complication to add an heterogeneity, or having just homogeneity is a necessary, unnecessary simplification? That we'll try to highlight given the upscaling theme of the this seminar or this conference. So one length scale we have from elastofriction. Now we are supplying from our side another length scale in the problem through the variation of the frictional properties. So frictional property may vary from, now the criticism is when in the earth we have such a nice sinusoidal variation in the frictional properties at the interface. We never, but from modeling point of view, a sinusoid gives me just one length, and in any other description of heterogeneity gives lots of other length scales. So this is just one wavelength. So I can actually see that how this varying wavelength interferes with already all the length scale that are already present in the intrinsic to the system. So one is naturally coming from the system, and one we want to test that what length scale interacts in which manner. So let's run this and see. So problem is again simple thin slab with rate state friction, but just the frictional properties are varying over one particular wavelength that is comparable to the elastofrictional length scale. So if you run, you see that now the convergence happen to place not at the same regime, but slightly not at the place where we want the earthquake to nucleate, but at place somewhere else, and it traveled a distance, considerable distance, and you find that it chose the most rate weakening region or in one part. So this is the part which is most slippery. All the fault is slippery, all the total interface, but it chosen one particular region which is most slippery, loosely speaking. So, and there we get unbounded sliding rate and that nucleus earthquake. Now we change the wavelength little bit, and we see that for a different wavelength, where we perturbed earthquake, the instability or the nucleation condition is satisfied at somewhere else, which is not the most slippery part of the fault. So you can clearly see that the including an heterogeneity and including an additional length scale in the problem interferes with the elastofrictional length scale to give richness of the, it's not straightforward that the most slippery region will take off. Also coming back to the point that Professor Bikas mentioned, that if we have two cracks in a same sample, the longer one will go, but if the cracks are evolving itself, and the shorter cracks can get kicked because they are reaching at the they are reaching first. So this is one crack solution, as I'm coming to this in a while, why this can be a solution, and this is another crack solution. And you see the one which is the short of whose length of the crack is small are the preferred region for instability to flourish. So that's little counterintuitive. So yeah, so point is I marked them by green part where they support lots of support flux of energy in that patch, or you can call it the earthquake nucleation around there, and these are forbidden regions. So let's try to understand. So now is the situation where you want to inject more physics into the system, like include pore pressure, include more variation in geometry. So you can complicate the system as much as you can, or an alternate route could be to let's understand why this is happening from a different perspective, or from maybe So we know this part that that sliding rate which we saw is scales as v square when in a rate weakening patch, given there is a sufficient length to do so. And so we can think ansatz for a solution of sliding rate as just one distribution over time to instability. And we see that and we just solve for these distributions. So if it's a homogeneous fault, throughout there is no frictional property variation, then one solution can be translated for translational invariance is there. So one solution is for all of the translate the faults. So there is one solution only. However, if there is heterogeneity, you break the translational invariance, and as a consequence, you get two solutions in this case. One at here, one at the top, and one at the crest. So this is consequence of just broken invariance in spatial that now you have two solutions for that, and there is method to how you can find that. So what to do now, that how to understand that this out of these two solutions, which one we should be going for, and which one maybe a evolving simulation will get into. So to do so, we now move to a self-similar system, because I forget to mention that these blow up, or the singularity is self-similar blow up, so we can exploit that property and go to find the similarity variables. And this is pretty much straightforward how we come from a time-like variable to a logarithmic of time-like variable. So you can think there is a singularity in the sliding rate. So we want to zoom in logarithmically therein and want to see what's the dynamics going on there, and that zooming in is provided by through this logarithmic lens. And if you just rearrange the equation, you see that it comes very naturally. I have the slide, but again digression, so I'm not going into. So now our system from physical position to physical time transferred to similarity coordinates, such that the x is remains the physical coordinate x, and s is now logarithm of time to instability. So this is the time remaining to instability. So in this formulation, we can recast the evolution equation sliding rate into a similarity equation, and the steady state or the equilibrium of this equation are the solution for the those instabilities. So this distribution is found by forcing an equilibrium on the similarity coordinate system. Anyway, and the point is now when we have two such solutions, we need to think that which one is the similarity solution. That's the usual case with similarity variable, that you tend to get more number of solutions. One way to do that is to think in terms of stability analysis of the solution in the similarity coordinates. So when we perform the stability analysis, there is a clear stability separation between the solutions here and solutions at another point. So you have, once you inject heterogeneity, you have lots of solutions. They are separated in their stability spectrum or in their spectrum. So some parts are associated with a unstable eigenmode, and hence they are not the ones where system will evolve to. So this is just like an attractor repeller kind of thinking. So you always attract towards a stable solution. So your simulations actually converge to stable self-similar solutions. Anyway, little one subtle point here, because you're in homogeneous case you have translational invariance as well as temporal invariance. Temporal invariance is also in the heterogeneous case. You get some other modes which you should be carefully figuring out, that which mode corresponds to which there are spurious modes that are injected from the invariances of the problem itself. So careful on that, you can actually separate the solution regimes. So going forward with the stability analysis, we can now see that changing the wave number has a stability pattern to it, that these solutions, the trough one, less slippery regions becoming more and more unstable, and hence unstable in the sense more and more repeller, and they are becoming more and more attractor. So unstable in self-similar coordinates means they won't be attained by the evolving sliding rate. So as you change the wave number from some number to as you go, so there is a stability, this part becomes more and more stable. So we expect that this part will always provoke or host or the preferable site for the instability or nucleating an earthquake. But if you keep on going, you see that they reach their peaks and the stability spectrum changes a little bit until you hit another variation or another wavelength of variation where there is an exchange of stability. So this is like classic bifurcation. You see nonlinear dynamics bifurcation where your stability exchanges about a point, so transcritical, I guess. So now the situation is that the least slippery ones, which were earlier least slippery, they are now stable. They are now attractor. And if you keep changing the wave number, there is a series of such transcritical bifurcation. So what I am bringing in this seminar is precisely because of the upscaling theme, that now you can see that there is a homogeneous limit. So that if there is a wavelength is large enough or wave number is low, then there is no variation as such, large and small compared to the elastofrictional length scale that system is applying. So homogeneous limit, there is no, so there is a homogeneous limit to that. And in the heterogeneous, very heterogeneous limit, you see you cannot distinguish between the peaks. So that tells that some of the wavelength over which frictional properties vary matters least if it is in this regime compared to elastofrictional length scales. It matters most when it is closer to elastofrictional length scales. So again, you can keep on borrowing our intuitions around this region. You see, if you have an external, if you have what we call, so those driven systems where your frequency or the time of time in which you drive a system matches with the external frequency, there is a resonance. This case is not that much different here. Your one length scale that you are supplying from outside is matching with the intrinsic length scale which is already present in the system. So you get a peak in the stability separations, and when you when that length scale separates from the elastofrictional length scales, then you do not then you get the homogenization conditions. So it matters most. So if, the length of variation that matters most when it is closer to the intrinsic length scale supplied by the system. Anyway, so there are more richness, so I am not going into that detail, but these unstable solutions are not all useless. They are in fact pretty useful ones. Now I can create heterogeneity such that I nucleate nowhere to find an earthquake or instability. So I create heterogeneities in such a way that so let me show the simulation. You will get the point that I create the heterogeneities in such a way that all the points are unstable. So it takes lots of time or delay to provoke an instability and hence an earthquake. So this unstable solution gives a way to do that. Just create a heterogeneity. So that tells that why maybe in certain regions we get a delayed earthquake, and so that the story is, I'm not going in that detail here. So let's move a little further. So far we didn't discuss much on the inertia part because we just focused on one realization of instability and not the dynamic propagation. So it's I changed the talk a little bit from Kaushik's talks yesterday for a, so if any system, maybe an earthquake or a landslide or thin slab, you can drive from left and then you can drive from the right, you can drive maybe together. So what situation permits, and there are important details that I didn't mention earlier, that it matters whether you start your simulations or your thinking considering whether your friction is at steady state or it's below steady state value. So let me show you some pictures. So here it's again sideways driven, and you see driven from both the sides, and you see in very like a, so this rate is meter per second in plate rate loading like 10 to the power minus 9 or 10 to the minus 8 meter per second, and you see there's a remarkable slow sliding. There's no instability here. It is actually way richer, that even though it's crossing the elastofrictional length scale, A over B is rate weakening, it still doesn't nucleate far till it coalesces, and then it becomes a source of seismic waves. So this is our archetypical slow sliding, which can be in rate weakening part as well. So that gradually builds up. Now this is the part you see the fault has become. So that was the instability that took it, and this is now the dynamic rupture. So this is interfacial dynamic rupture. At this stage, your fault is actually radiating energy into the bulk, and that's what seismology carries. Okay. Now let's see another side loading condition, like here. So I think this is another, but here you see fault is long enough, and you see there is a breathing kind of a situation, like a Sine-Gordon breathing or not. The details are yet to figure out. These are unpublished results. So it may be Sine-Gordon kind of a breathing thing, and before an instability kicks. So this is not instability yet. This is the instability which we just saw previously, and the propagation of this rate was the which we didn't discuss much. Yeah, here. So this part we didn't discuss how it goes, but we discussed that, and then we didn't discuss the so let me go to another simulation if I may. So again, this is another fault, a side loading. Yeah, this is now loading from one side, and there could be scenarios where you do not nucleate earthquake at all, and you can see there is slight peak. Yeah, so here there are here we nucleate a dynamic rupture after traveling this much of distance, sideways loading. So that was the point, that because we have a lab-based, maybe the interfacial frictional conditions are the ones which is sideways propagation are actually manifesting to both ways propagation later. So there are details in here. So let's go to. So my point is, the way an earthquake becomes fault and a fault becomes an earthquake like is that there is a slow sliding phase and there is a colorful instability, then there are dynamic ranges. Okay. And so I think that I'd like to stop here, and I thanks for your attention. That it's not very different, the different natural systems like this Kelvin-Helmholtz instability, Rayleigh-Taylor instability, they are all driven, as mentioned in the famous papers, that the differential activity generally leads to instability. So it's not very different in cases of earthquake. These are the differential, this is the differential rate of strengthening and differential rate of weakening is facilitating what earthquakes like instabilities are. So I thank you for your attention, and yeah, I have a little summary that earthquake nucleation, here we model as elastofrictional length scale, slip rate attains in finite time, and this is the indicator of a condition which provokes the nucleation. Yeah, and heterogeneity introduce additional length scale and hence an additional dynamics. So yeah, thank you for your attention. Yeah.
Thank you, Soham. We have a few minutes for some questions from the audience. So a couple of things to maybe get started. In the first part, you spoke about this regularization, right, where you had the strength dependent on the slip.
Yeah. Yes. So I have additional slides for that. So again, yeah. So this you can actually do a bit manipulation before going to experiments, then you can find that this is ill-posed problem, and by just slightly tweaking and introducing a length scale length there, you can, I think I do not have that slide right now, but yeah, that is possible to regularize. Yeah.
I see. Okay. And the second case, when you had this inhomogeneity that was there,
Heterogeneity.
the heterogeneity in the frictional interface, right? That the rate and state law, that A by B.
Yeah.
The instabilities, those sequence of transcritical instabilities that you showed.
Yeah. Come again.
The sequence of transcritical instabilities that you showed, right? For
Yeah. Bifurcations.
Yeah, the bifurcations, transcritical bifurcations. Is that independent of the amplitude of the heterogeneity?
Depend on the amplitude of the heterogeneity or not?
Yeah, the amplitude of the heterogeneity you put here. Because there will be one more scale that might be important, I suppose, right?
Yeah, so then there is actually, you open the can of worms there.
I see.
So I keep one particular amplitude and just played with that.
I see.
So yeah, that matters a lot.
Okay, and so if you had, for example, these are for single wavelengths.
Single wavelengths, yeah.
If you had, let's say, two wavelengths, like one large and one small, then will the instability onset will
one which is closer to the
elastofrictional length, and one that is slightly away.
Scale, yeah.
Okay, so then it will always try to
come to that.
Come to the elastofrictional length scale. Is that? I see. So can you think of that as some type of equivalent crack size for something to start?
Yes, so this bifurcation diagram I forget, so that's what happens when you make the slides at the end, end moment. So they correlates with the length as well. Length of this length, if you plot, it takes this form. Always the shorter cracks, short length cracks are one nucleates.
I see.
Yeah. So I mean, I should have those results. Yeah.
Okay. Yeah. There are lots more details.
Yeah, there are tons of details in here, but that's what suits best for the seminar. It's a fracture as well as upscaling, so that's the only way I can accommodate both of. And so there's a wonderful YouTube seminar going on called as Tectonic Fear, which you may know. So there are lots of details about the fracture energy, the breakdown energy, their separation, seismological conditions, and lab experiments to demonstrate there is a difference between fracture energy, breakdown energy literature. So I refer to students, anyone here who are interested to the earlier part may please refer to that. Yeah.
Any other questions maybe from a couple of more minutes? So you said the last part of the work is not yet published, is it? This part, the heterogeneity part.
So I mean those are in conferences. I'm not in a paper conference, but presented. But I should have completed 3 years back, but you know how things go.
All right. So if there are, you have a question? Okay. If there are no other questions, then please join me in thanking the speaker again.
Yeah. Thank you very much. Oh yeah, I forget to thank initially. I think I should have mentioned this earlier. So so the acknowledgement goes to Robert Vieska, my advisor, and Dimitri Garagash, my postdoc advisor as well. Thank you.
We have maybe 9 more minutes. Maybe we can just wait. So if people want to come in at 12, they can do that. So.
That's turned on now? Okay. Yeah, maybe it's all the way.
Okay, so our final talk in the morning session will be by Jordi Barro from the University de Barcelona on quasi-static kinetic avalanches in SOC in deviatorically loaded granular media.
Hello, everyone. First of all, let me thank the organizers of this talk for their hospitality, receiving me here, and especially because I got the opportunity to meet personally, let's say, and put faces to the authors of so many papers that I've been reading during my career, right? And until now, I couldn't have the opportunity to meet you, so thank you very much. So I'm going to present today's work that was published a few years ago with this title, Quasi-static kinetic avalanches and self-organized criticality in deviatorically loaded granular media. It was published in PRL in 2021, and is a work that started as a collaboration between two groups in the University of Calgary at that time. The group, it was the group by Jorn Davidson, where I was working in complex systems, and the group by Richard Won and Mehdi Puraga that was on civil engineering, right? So it was an interdisciplinary work. The point I finished this working on Barcelona when I was back in Barcelona. That's why I'm acknowledging as well the financial support there by AXA Research Fund. And now that both Mehdi Puraga and me were postdocs at that time, now we are more on tenure track positions, and we had the opportunity to secure some funding thanks to the NSERC and the Spanish Ministry of Science and University to follow this research. That's what I am retaking this, right? I added this subtitle, Upscaling Dynamics from Isostaticity to Soft Matter, just to put into the context, right, of this upscaling in complex systems. That is the topic of this Fracmeet meeting of 2024. Okay. Just to begin, I will give a summary. First, I will start talking about these problems of upscaling, this idea of the stability when we talk with fragile matter or granular matter. Then I will talk about the simulations that we used, DM, so discrete element models, right, to define these kinetic avalanches and to identify these avalanche phenomena. On the third part, I will talk about one specific result, that is we found this criticality in a kind of a stable evolution state that I will explain in a moment what it is. And fourth part, I will go to the global aspects and talk about how we found this non-universality of exponents that I will found here in the part 3. Okay. So first of all, let's talk about this upscaling in complex systems in a general way, let's say, especially in this problem of stability in fragile matter, right? So this is a work by Cornelius Escher. You're probably familiar. It's called Metamorphosis, and I think it illustrates pretty well what happens in complex systems, right? So we start in a system that we understand and we understand well what is happening here. These are some birds, but as soon as these birds start to interact together, right, we get these murmurations, we get these nonlinear behaviors, right, in general in complex systems, that mutates, let's say, the system in something that it's hard to be recognized, right? So essentially, we have problems to find ways to explain or to model this kind of phenomena. But if we scale it up enough, sometimes, I mean, our mind has this miracle, let's say, that is able to recognize patterns everywhere, right? And this is this quotation by Whitner that you have here in this school, right? That how we are able to use mathematics to be able to recognize new laws, let's say, and new descriptions at a higher scale, right? That probably has nothing to do with the description that we had at lower scale, right? This was an idea that was introduced especially by Phil Anderson more than half a century ago, right? And it was the basis of his critique to the constructionist reductionism. So in his work, he said that the ability to reduce everything to simple fundamental laws does not imply the ability to start from those laws, let's say it's birth, right, and reconstruct the universe, right? That's why we usually approach from an empiricist point of view, same problem at different scales with different representations, right? And this is a little bit what happens when we talk about this fragile matter problem, right? So from a static equilibrium point of view, if we have hard spheres, let's say, and we want to put them together in a box that they maintain equilibrium, static equilibrium, this is a purely geometrical problem, right? So it can be solved with this Maxwell construct, right? Setting that the number of constraints has to have a certain relation with the number of particles and the dimension, right? On the other hand, when we talk with large system of particles, and especially when this is soft matter problem, right, that we identify this static situation as this idea of the jamming transition, right, that we are able to represent in terms of thermal noise, of, for example, this deviatoric stress, and the porosity of the system, or the density of the system, right? We identify this surface here, this kind of manifold that contain this jam state situation, right? And in between, that's a problem, right? We have a void between these two extreme representations that we try to fit, and in fact, much clever persons, authors, I mean, like Edwards, Blumenfeld, and Ball, okay, they try to find this kind of parameters that are able to reproduce or to explain how granular matter behaves in terms of like a thermodynamical system, right? So this is the underlying problem, is how to upscale between this hard space description and the soft matter description, the thermodynamical scale, right? And this is something that is non-trivial. I mean, this is how Randall Munro described it after talking with Karen Daniels, right? That this is like, describing sun is like one of the hardest problems that you can have in physics, right? In general, complex systems, right, are very hard to explain. So this is something that I try to stay away for it, but it was the matter of concern of this person here, of Mehdi Pourave, who at the time was a postdoc in Calgary in civil engineering department, right? And now he's a professor in the university. Now he's a professor at the University of Carleton University, in Ottawa, right? So he had this engineering formation, so he's an expert, especially on these stability problems in complex environments, right? And he come to an idea. I try to summarize it here, but I'm not the expert on that. But the idea is the following. I mean, imagine that you start with a granular system that is on a static equilibrium, right? And you start to compress it uniaxially, right? Now consider that you have two different configurations here. One is loose assembly, so it's below, let's say, the stability, the stable density, and the one is above, right? So this is dense. This is just a 30% difference between one and the other on the density of the particles, right? So this is over-densified, and you see that the over-densified case, you have first strengthening, and then you have this force weakening regime, right? And then on the loose assembly, the particle just keeps pushing one against each other until you get the same stationary regime, right? So from a mechanical perspective, you have like two different paths that brings to the same stationary regime. This is also non-monotonous transition, right? And this is something that, of course, just looking at the stress strain, we will be unable to reproduce this kind of behavior, right? So he realizes that if we look at it from a different perspective, looking at the geometry of the contact forces here, at the contact between particles, you can see a different picture, right? And it's that from the loose assembly, you simply start with low coordination number. That means the particles are loosely connected, and then they start to grow a little bit to this limit, while this Fibrek anisotropy is increasing. This is just the anisotropy of the direction of the contact force, right? So we are going towards a regime where the contact seems to be organized in a certain direction, right? On the contrary, in the dense part, we start at high coordination number, and then we lose this contact very fast. In fact, this is this line here that is losing context by increasing as well this Fibrek anisotropy until we get this tip here of anisotropy, and then it goes back, right? So essentially, this final point here seems to lie inside a kind of a limit surface here. And if we add here the rigidity ratio, he found out that you can build this manifold that is very similar to this idea of jamming, but that it works well in these intermediate scales, right, of granular matter. Right? And in fact, by performing different kind of mechanical tests, he observed that they all seem to evolve towards this final state, this final we call this a stable evolution surface or a stable evolution state. Right? So how this is the idea he had in mind when he realized that we were a group working on complexity science. He addressed us and we tried to study this. He had different problems that what I'm going to talk about, but initially, I mean, the first thing I observed was this, of course, these fluctuations there at this final state, right? Because I was working on avalanche dynamics, and this is something that is not common in engineering. In engineering, I mean, it's very easy to disregard this as noise, a simple noise, but in physics we know that this is something different, and this could be the underlying 1 over f noise, right? That simply, if you look at the spectral density of this noise, we may identify power law relations, power spectrum, let's say, and this happens at different scales. This is observed for very simple systems like interconductivity of vacuum tubes or superconductors, to the pulsation, let's say, or the rates of the noise on the heartbeats, or even in a single neurons, in the brain, in the activity of the brain, right? In magnetoencephalograms and electroencephalograms, and also in decision making for even on the noise, underlying noise of compositions and the cognition of human for the human condition, right? In general, we develop, so during the 80s, the authors developed 2 different explanations to that I would say they are complementary, depending on the systems. One is this is the outcome of adaptation, the other that is the outcome of self-organization. So essentially, this is the idea of developed by the people on Santa Cruz, right, that adaptive complex systems, which are systems that are really complex, that are able to self-organize themselves into a way that they can survive in difficult environments. So what we'll say, let's say, an intelligent system, right, tend to organize towards this regime, what they call the edge of chaos, that is where fluctuations seems to progress, not indefinitely, but they don't explode exponentially, which you would expect in a chaotic system, and don't die fast, right? So you identify here as something related to complexity, criticality in terms of statistical physics. And in parallel, we had this idea by Perbac, right, of self-organized criticality. It says that identified that even simple systems like a pile of sand or a pile of rice, this is the Oslo experiment, can exhibit this transition towards this critical behavior, this ping noise, so this distribution of noise like this, that we can explain in terms of avalanche dynamics, right? So essentially, here when we usually talk about a spontaneous system, here we talk about externally driven system, and I mean here we usually consider continuous signals. Now we can study this in these systems as punctuated or intermittent events. That is what we call the avalanches, right? And just allow me this little joke. If this is the root, let's say, of intelligence is in adaptation, let's say, and self-organized criticality is like the seat of these adaptations, right? I would say that the group on Oslo could be the parents of artificial intelligence, right? Somehow, but I guess this is more on the philosophical side. Okay, so going back to the data. So what we do is to perform these simulations much slower. These are discrete element model simulations, and you see that this noise then is more spiky. I mean, you see that this is shorter in time. This is a good trademark of the presence of avalanches. Let me play a movie here. So this is a little bit what I'm showing there. So this is the deviatoric stress. You see that whenever we have this noise, we see a drop in the deviatoric stress, right? So it seems to accommodate the stress more equitatively, right? And at the same time, we see an increase in the kinetic energy inside the particles of the system. So here I'm showing the the actual sample. These in gray, these are the grains are difficult to see. The important thing maybe here is these black lines here. These are the force chains, right? This is how the force is structured through the contact points and distributed. And you can see that during the avalanche this is changing, right? The amount of stress that are supporting this change is changing. And then the color, this is the kinetic energy of the particles that well, it's just coarse grain, but you can see that, and that's the interesting part, that the kinetic energy can start, so particles can start moving in some place, but then rapidly move to other places and can go all around the sample. And this is important for what I'm going to explain later. In any case, I will have this running. Yeah. They change, I mean, especially change in this case, probably there is no backlink, nor clear slide. Let's say the particles are small, right? And they just transfer a little bit of stress, let's say, right? I mean, there is, yeah, you don't see here, I wouldn't say that there is, well, maybe just some fortunes are breaking. This means that we have some contacts, losing some contacts during the avalanche, right? But very small one, not the large ones. Yeah.
Okay, thanks.
One more question. So do you have friction?
Yeah, sorry, this is our with friction. And I will explain just in a moment. It's with friction and elastic particles, right? In the stages. Okay. Okay, so this gives the idea that indeed we have avalanches here, right? And we are going to want to find some way to characterize them. Okay, so first of all, to see if really we are detecting avalanche here. And there's an interesting question that we couldn't address, but we would like to address at some point, is whether we can define the states from this idea of SES instead of the traditional jamming representation. And what we are going to address here is how these avalanche statistics are in this SES, and what we can talk about the system and the nature of this stability limit, right? So this is the second part, is on the simulations details, right? So essentially I will focus on how we identify these avalanches during this quasi-static biaxial compression of compact granular assemblies. So what we do is the following. It's the same experiment as before, so we compressed vertically at a constant rate, a constant strain rate, controlling the strain, and then we confine this at a constant pressure, right, on the lateral bonds, right? But what we add here is to add this quasi-static condition. So first of all, we drive the system very slowly, so there is very little inertia to the system. And when we observe that there is a jam in the kinetic energy, we stop the driving, right? This is represented here. We stop the driving, then when it goes above a certain threshold that is defined by the expected affine deformation, or affine deformation of kinetic energy here. And then when it goes above, then we stop the driving, and then we resume it when we believe that all the energy is dissipated already. Right? This is a method that was developed by Mark Robbins several years ago. Okay. So what we will do is to play with the parameters. So basically we control 4 different parameters. One of them is the size of the sample. The number of particles will be quite trivial. It's just a scaling relation with the results, right? Here is the initial porosity. This is what defines whether we are in a dense or loose assembly, let's say at the beginning. Surprisingly, it looks like the statistics doesn't change much depending on the initial porosity. Once we hit this SES, it looks like everything the statistics are the same. The driving rate has no effect at all, just on the limit to detect avalanches. So this implies that we are indeed in this quasi-static regime where we don't see inertial effects. And the most important aspect here will be the confining pressure, right? So how much pressure we impose by the lateral bones. And this has a direct relation with the rigidity of the particles. The higher the confining pressure, the lower the rigidity, the softer the particles are. Right? And this is what will have a most relevant effect on the statistics advance. Okay. So now what we do, first of all, is to look at the energy balance. So we want to understand these avalanches from internal measurements of the sample, not from the external ones, because we may miss something on the external measurements. And then we see what happens here is that we are inputting energy through work by external driving, right? And this is dissipated. Well, first of all, this transport increases the strain, so the elastic energy on the context. And overall, sometimes we have this release of kinetic energy that then is fast dissipated, right, by viscous drags that is proportional to the velocity and frictional forces, right? And also, this is important, we have to add here the presence of this work that goes to the lateral walls, right? So essentially, what happens is that since we are not considering any heat, this is a thermal condition, so all the work that we apply finally is only transferred to the lateral walls or transforming the internal elastic energy, right? Now what we do is to define these avalanches when we detect these jumps on kinetic energy, because we want to describe it in this way as a point process. So we have an intensity of these point processes defined like instead of time we're using these displacements, so we don't have to worry about these times where we are stopping the driving, and also we can put it in terms of the stress, right, on the upper bound, sorry, in the vertical direction. And we define this mark, the duration of the avalanche. We don't take the whole relaxation. We just take the time of the stress drop that coincides more or less with the energy drop, with elastic energy drop, right? These two magnitudes are measured as well. And the kinetic energy, what we measure is the peak of kinetic energy, right? Is this jump here, and I will explain it in a moment why. And then we measure as well the lateral work. Well, this is related as well with the amount of dissipation during the avalanche, right? These are our marks that will define these avalanches, and we will try to find out which are the statistics and what are the measurements that we are interested to compare with what is traditionally measured, let's say, in avalanche models. So considering this elastoplastic theory, right? So when we talk about the avalanche, we usually reduce to consider a system that has some slippage, and then we consider this velocity profile. Usually is arrested, then it jumps and displaces, and this is the avalanche. We consider the size to be like the amount of displacement. This will be a mean field measure, right? That we had over a certain duration, and the energy we measure as something that will be proportional to the kinetic energy that has been released, right? That is with the square of the velocity. And also this is another measurement that can be interesting, is this energy peak. It's like this peak of kinetic energy that is just the maximum value that we observe in this avalanche, right? Now we want to compare this with our simulations, right? And this is, we'll spend a little bit of time here just to look how we can manage our data to fit it with these ideas here. So we start just by looking at considering an stability problem, right? And the expected relation that we should observe between the internal elastic energy and the stress drop that we observe in the avalanche, right? So essentially, we would expect that variations of the internal elastic energy scales like this, so linearly with the stress drop, right? And considering these terms here, so essentially here normalized by the stress ratio from between the vertical and the lateral ones, and here is just, I mean, what we would expect to be this internal work, right, that we are performing here. This is the Poisson ratio. Here, these are the elastic, the mechanical elastic constant, right? So essentially, what we perform is this approximation that the volume goes like this, considering that these are spherical particles, right, and has the porosity here, and also that these elastic parameters we can reduce them, so the effective elastic parameter reduces as a function of this density of contact points, right? And we end up with this expression here, so this scales linearly with the n, with the number of particles, and well, we expect this linear relationship with the strain drop, with the stress drop, sorry. And then we have this scaling term here that goes with the square of the confining pressure, and this element here that could have some dependence, some additional dependence on on the confining pressure, and this is what we are plotting here. So here I'm trying to find out if there is something missing something there, right? So essentially what I see is that this term here essentially goes with confining pressure square a little bit less, 1.91. That means that there could be some minor dependency that I'm losing here, right? And then when we look at the avalanche, so we look at the distribution of avalanches, and we try to normalize all the strain drops by the stress release, right? And we find this linear relation. So we see this linear relation between both, right? We lose something for the small avalanches. This is normal because we have some detection bias, right? Because small avalanches need to be a certain way in order to be detected. But when avalanches are large enough, we recover this linear relationship. And these lines here are just the predictions from this scaling. We observe that this is not exactly this confining pressure with the power 2. It's a little bit less what we need to impose here. But again, this probably has to do with this little bit of variation with this term here with confining pressure, right? And what's interesting is that if you consider the elastic energy drop, we see that this linear relation stays here. Of course, when we compare this with dissipation, with the dissipated energy, we see that, okay, for large avalanches, this is more or less the same, but especially here for avalanches at low confining pressures, we see that this doesn't stand. So dissipated energy doesn't scale well with the stress release. And this is important because usually this is what is reported, right, in other systems where you don't have movable lateral walls. So if you are in isostatic conditions, then this will be the same as this, but now here we have some work that goes to the lateral walls, right, and this is what causes this difference between right. Okay. Now, it's interesting to see what happens also to this word, to this lateral word, because I don't know what you will think will happen, but we have two different types of avalanches we identify. Some avalanches that are caving in, let's say, the lateral wall. So the lateral wall, so the stress at the lateral walls decreases, so they have to push in to maintain the lateral stress, right? And some other ones that just expand the lateral walls, right? So just increase the expand on this direction. This is typical for, so this dominates for low confining pressures, and this dominates, so it means for stiff particles, and this dominates for high confining pressures, it means for soft particles, right? And the interesting thing is that here you see that there is a linear relation between the work and the elastic energy that is released during the avalanche. But here we find a relation that goes with the square of the elastic energy. This is something that we didn't understand. Okay. So regarding the energies, what we take for energies is this measure of the peak of kinetic energy. That you will imagine that this will go with this B2 square, the maximum value of the B2 square, right? But the point is that in this elastoplastic theory point of view, usually you consider overdamped systems, right? And here we have a lot of inertia. In fact, here, very little, I mean, you see the characteristic time of dissipation is much larger than the peak, let's say, of elastic energy, of kinetic energy, and the drop of elastic energy. So we believe that in fact, we are in this situation where what we're measuring is actually what it will be the E in elastoplastic theory. And we can look at it this way if we consider that the velocity is proportional to U dot, so the derivative of U, of the internal energy, then this energy should be proportional to the integral of this U dot square. And in fact, this is what we found, more or less, a very good relation between both. So probably what we are saying is that these energy peaks give a good measure of the energy of the sample. Okay. So now looking at the temporal properties of this system. So first of all, what we observe is that, well, we look at the inter-event times instead in terms of elastic strain, of the external strain, right? So first thing we observe is that we have an exponential tail for large inter-event times. It means that we are in a situation where more or less avalanches are stationary in time. But also we observe for short times that we have some sort of regularity. So this is not exactly an exponential. This has this drop here on the statistics that we will expect, and this is usually a treatment of some sort of pseudo gap, right, in the residual stresses on the slippage, let's say, right, that you need, the residual stresses that you need to activate the next avalanche, right, and this fits well this gamma function here, right. That probably implies that we have this power law distribution of pseudo gaps close to the failure, let's say, to the stress that we are dealing with, right? We can use this, since we are in finite systems, to try to elucidate the nature of this SES, of this stable evolutionary state. So in terms of this predictability, this is an idea from seismicity, and is that when we are, so suppose that avalanches are triggered at a stability limit, then what will happen is that we drive the avalanche, then we'll have an avalanche of a certain site, and then we will need to load a lot, let's say if this is a long avalanche, we will need to drive it a long time in order to have a new avalanche. So it means that avalanches are time predictable. If you know the size of the previous avalanche, you will know the time to the next one, right? On the contrary, if you consider that this is a kind of a stability basin, right, and then avalanche, the system can progress arbitrarily far away to this stability basin and then can go back then. So it means that the times that it takes to load will be proportional to the size of the next avalanche, right? This is what is called sleep predictable avalanche or size predictable avalanche. And we compare this with our data. We simply perform here, so looking at the times before and after the avalanche, right, and the sizes before and after the avalanche. And the state, sorry, the external stress, and what we observe by looking at the autocorrelation function is that the ones on top are more persistent. This implies that we are closer to a situation where the SES is a stability limit, right? When we get to this SES, then avalanches are triggered, and then we are in a situation of time predictability, right? You can understand it better maybe looking at this distribution between the waiting time and the size of the avalanche before and after that waiting time, and you see that clearly that you have here a linear dependency. I'm showing here all the cloud of points because you see that there is some kind of gap here. So essentially what you observe is this pseudo gap, right, that we seem to observe that we are missing loading times that are smaller than the previous avalanche to this power law here, right? So it means that the SES probably we are closer to a stability limit triggering this avalanche. Okay. So now the third part will be on these results that I want to focus, and has to do with the topic of this talk, and is the existence of avalanche criticality at this stable evolution state. Right. So remember this example I showed before, right, with the two examples, the dense and the loose assemblies. Here I'm showing as well where this activity is happening. You see that for the dense assemblies, activity is focused in shear bands, so that this doesn't happen in the loose assemblies. The activity is all around. At the end of the day, it seems it doesn't have any kind of effect to the avalanche statistics that we observe, right? So here what I'm showing is with lines and these different dots. With the lines is the distribution of kinetic energies that we observe during the whole, this whole interval where the system stays at the SES. And here is the same with elastic energy drop. And you see that both simulations go with the same distribution. They are very similar. And furthermore, you see that here are very different stages of the strain stress curve here, with these markers A and B, and all of them seems to follow the same distribution. So in essentially, what I'm trying to say is that this is stationary distribution, right, that doesn't change over time. Once you hit the SES, all avalanches fall within the same distribution, right? We may wonder what happens with this modulus here that is negative and this one that is positive here, how it is possible if the distribution is uniform. So we look at these Pearson coefficients of this effective modulus with the activity rate, the number of avalanche over time. We see that we have some correlations, and also this reload, let's say that we have the speed of reload that we have on sigma y. We see also a positive correlation and very small correlation with the avalanche size. So actually what is happening here is we have more avalanches than here, right? Not that they are stronger. Okay. Okay, so now if we want to study all the simulations together, we find, here we have the results of different distributions on internal energy and kinetic energy. And you see that we need to find different ranges if we want to find the exponent here, right, to compare this power loss, right? So what we did is to consider this scaling relationship. So this is a power law with some characteristic form, so characteristic shape, right? And that this shape has a characteristic scale that goes with some power law exponents. So this essentially for the sizes, this will be the 1.85 that we seen before, and this will be 0.5 that is equivalent to a fractal dimension of 1. To get this, right? So we try to fit this exponent just by plotting the bivariate distribution, so with these averages here, and try to fit them together by writing these new variables, right? And we observe a good fitting within a certain area that is independent, that is not affected by small size effects nor finite size effects. So the resolution limit nor finite size effect, right? We use this to scale our distributions, and then from here we define the range where we are going to measure these exponents by maximum likelihood estimation methods. So we have these three exponents here. This one that describes the relation between k and delta u. We have this one here that is the distribution on u and on k, right? And then if you look at this, we find this relation that, so essentially what we observe is that the only parameter that matters here is this confining pressure, right? Remember, high confining pressure means soft particle, means low rigidity, low confining pressure means high rigidity, right? So here in blue, I'm showing the exponents of the size distribution of these energy drop, these elastic energy drops. And in red, I'm showing the energy distribution, so these kinetic energy peaks, right? This is what we should expect with the mean field theory. We will expect this 1.5 here and this 1.33 here. And you see that for low confining pressure, especially for the red one, that is the one that we have a longer range to integrate over. We see that for low confining pressures, we see a very good agreement with the mean field theory. But as we increase confining pressure, we observe that this goes down to these values of 1 that are closer to what is detected with elastoplastic theory, right? With these models where you consider 2D systems with soft particles, right? And well, I mean, this is like important result, right? That we see a transition depending on the stiffness of the particles, of this rigidity. Essentially, it is that we observe stiff particles, we find mean field solutions, and soft particles, we find this elastoplastic theory. And now I just wanted to spend some minutes explaining how we can explain this, at least how we can explain that some non-mean field systems have mean field exponents. And if you were in Andhra Pradesh last week, you know where I'm going on, where I'm going to explain now a little bit. So this is so just to remind about the mean field theory, right? This is a way to introduce it is through the Ising model, with a random field Ising model, right? That is simply consider the Ising Hamiltonian, introducing an internal field to each one of the sides. And the mean field model will be considering that all these interactions, of course, are all-to-all interactions, and we can represent it as a single field. And then, in fact, what I will say the mean field is this H plus M, this contribution, and then every time that we have a flip, we have an increase of 2J over M to this mean field value. Okay, so this is a way to represent it. When we have a flip, when we get one of these H values, we will increase by 2J over N the field, right? Then if something else happens, some other field falls within this increase, then this will increase again, etc., right? If we want to study this in integral differential equations, let's say it will be complicated, but we have another tool here, and is to study this as a branching process, right? And this kind of mean field behavior is exactly a Poisson branching process. So avalanches grow as a branching process where you have the generation is a measure of time as well. And if you go thermodynamical limit, this mean field avalanches we observe at this Poisson, Galton, Watson, right? And I'm adding here, this is the exact solution. This is a Borel distribution, right? This is the exact distribution of sizes. And this was reported already by Sethna, but this also was reported by Alex many years ago. I mean, when they were looking at this fire bundle model solution, this is what is called the forward, I think it's the forward rule, let's say, the forward propagation rule, right? And it's a little bit hidden, but this is exactly the same result, right? This approximates well with this power law relation with exponent 1.5, right? Sorry, there is a typo here. This will be energies. This distribution of energies on the mean field, this mean field will be this minus 4.3, that is this 1.3. Here is another typo, this should be a 2. This is a minus 2, but we won't look at durations at all, right? The point is that these exponents here are not exclusive of the Poisson-Galton-Watson. These are common for all memoryless branching processes, right? And what happened now, imagine that instead of having a mean field situation, we have something like this, where the connections, instead of being nearest neighbors, they are random. So this is rewired in a way that is very hard, let's say, to go from this propagating to this spin, and then going back to a neighboring spin of this one, for example. What we are doing is to break potential loops that you have when we are restricted to this system, right? So by doing this, the avalanche can grow as a percolation process, and now the cluster size or the avalanche size grows as a tree as well, but more similar to a binomial Galton-Watson, right? And we still have these the same exponents, very similar exponents, right? And this has been observed in different systems. For example, I mean, in processes where in simulations that seems to break these loops by some way or another, like this works by Peter Grasberger, or this from the group by Ferenc Kuhn. Okay, so what's happening in granular matter? Probably what is happening is something like this. So this is some results, experimental results by the group by late of Beringer. And when they observe this is an impact of particles to a granular medium, you see that as you increase the stiffness, these 4 chains that we are looking at, right, here, it looks more like an actual network for high stiffness, and for lower stiffness is more smooth, right, and dissipates sooner, let's say, in more ordered way than here. Here it becomes a random network almost, right? So probably this is what is happening in our simulations, is that when we are considering stiff particles, this, and just remember this, that we observe it here, that the activity, instead of staying in some place, it moves around all the system, right? It can translate and then break potential loops between the dissipation of the avalanche, right? And this is something that can happen as well with porous systems. So this is these are simulations by using finite element models, right? But introducing these pores, random pores. This is from a group in MIT. That they perform these simulations, and you observe that the stress, when they stress these samples, it also focuses your channels through these kind of force networks that are very similar to the ones with porous materials, right? So, and this gives the idea that probably can explain other legacy results that I had. This was working during my PhD with Eduard Vives. What we did was to compress uniaxially some rocks. In this case, it's not exactly a rock. This is a silica glass that is very tough. It's very fragile. And then what we do is to detect the acoustic noise that it's emerging from these fractures. We report these signals. We integrate this to get the energy, and then to make the statistics of the energy of these signals. And this is, of course, a very porous material as well, right? And what we observe, again, is this power law distribution of energies with an exponent that is quite close to this mean field, to what is predicted with mean field theory, right? So essentially, this is what we would expect. So this would report instead of 1.5 a little bit higher, but we are very close to these mean field predictions. What happens is that in this case, when we try with different materials that are softer, instead of going down, the exponent goes up. That is something that we don't understand either. But we observe both a dependence on the composition, so in softer particles or tougher particles, and also in the porosity of the particles, right? And this is something that is interesting to see, that this exponent relations, these non-universal exponents in the distribution of energies also happens in these compression experiments with fractures, right? Okay, so that's all. I'm right on time? Good on time? Yeah, okay. I wanted to explain. So first of all, first conclusions is that we try to identify these avalanches by doing this connection with internal measurements, that we find that these elastic energy drops serve as a good measure of sizes, and the kinetic energy peaks have a good measurement of these energies in terms of traditional avalanche dynamics. Then we identify this stable evolutionary state, right? And we see that this behaves not as much as an attractor, but a stability limit, right? Where we observe these SOC avalanches, right? So it seems like it has properties of self-organized criticality, as we expect in this mean field theory as well, when you consider sleep avalanches, right? And but it's not exactly mean field, of course. We've said that we have these non-universal exponents that matches these mean field models for stiff particles, sorry. And but for soft particles, we obtain these to the exponents expected into these systems, right? Finally, this explanation that I gave about the mean field exponents, that probably is due to the fact that for stiff particles we are closer to a branching process, to a memoryless branching process, and that may occur due to this structural heterogeneity of these force networks, and that we could explain maybe the same, probably the same explanation for the acoustic emission experiments on fracture as well, right? So for some samples we have mean field theory, and not from some others. So now we are trying to address these different problems. First of all, to understand what's happening with this expanding and contracting avalanche that we observe, right? When the walls cave in or expands, depending on the kind of avalanche that we observe. Also, we want to verify whether this transition is smooth or is just sharp, and it's just a matter of finite size effect that we observe at this intermediate stage, right? Shall we go from one universality class to the other, or we have a smooth transition between them, right? Then what we want to look at as well is to determine these avalanche properties at SES, and in terms of these measurements, like anisotropy and fabricant anisotropy and coordination number, and outside SES, if we're able to have another statistics outside the SES to see if we observe a transition toward criticality, right, with these methods, right? And from this we want to compare as well if we can change, let's say, the potential energy landscape and the kinematics or the inertia of the system, try to identify secondary effects that have been discussed in the literature, right? This is just a summary of the bibliography I've shown. Also, I would add that if you want to know more about this idea of the SES, there is a talk by Mehdi Pura, who was the author of this idea, that you can check, right? It's around the time. This is not the length. This is just the time you have to move. It's around 3 hours at the start. Okay, so thank you very much for your attention.
We have time for some questions.
Yeah, nice talk. So 3 things I wanted to ask. So one was about comparison with frictionless systems, because there's a lot of data on frictionless system in the quasi-static limit. And then also for amorphous materials, a lot of data, similar data. I mean, so do you get similar exponents? For example, Salerno Robbins, they're doing it for shear, you are doing it for compression. So does the protocol matter? So because in the later part of the talk, it seems that protocol wouldn't matter, right? And the third would be what you just now mentioned about the kinematics, the dissipation. So you have chosen one model of dissipation in whatever the work that you have done. If you choose underdamped or different kinds of dissipation modes, how would the exponents change? Do you have any thoughts?
I don't know about that. Yeah, I mean, first of all, yeah, of course. I mean, we are comparing at the beginning, right, with frictionless particles, and then, of course, the introduction of friction and elasticity on deformability, it's what breaks this idea of isostaticity, right? I mean, and that's the key, right? That and this is something that, I mean, maybe will be a better person to answer this, but yeah, I mean, that's the idea. I mean, what we are trying to do is to extend these ideas of isostaticity towards the limit of soft matter, right? And in between we have this area of fragile matter, right? That is the one that is hard to cover, right? And with this different idea, we're trying to approach the problem by different ways. The second question was on the driving, on the driving protocol. So notice that the paper is deviatoric stress, right? So that's the idea. I mean, at the end of the day, it doesn't matter that much. At the end of the day, the events that we have are deviatoric. I mean, they're just shear events, right? And it shouldn't matter that much that you compress it or you just shear it, right? Because you have the formation of the shear event.
Robins would be useful. I mean.
Yeah, that's. I mean, in fact, we have, of course, more comparison in the paper, but yeah, I mean, this is the idea, right? For them, they obtain these exponents there that are around this 1.5, right? I think 1.25, sorry, 1.28, and yeah, I mean, that's the idea. In their case, they were comparing a set of elastic energy drops. Why I showed this with Salerno-Robbins is that, they were comparing a set of energy drops dissipation. But it's because it's exactly the same in their case, right? Because they are using constant volume, right? That should be the same. So yes, this is a measure that should be comparable with theirs, right? Yeah. And the last one is that we need to do more experiments. I mean, to play with different parameters, let's say, right? To say about different dissipation mechanisms. Of course, we are using, for example, elastic particles, linear elasticity. It shouldn't matter that much, but of course, if you use Hertzian interactions, it could be different. I mean, I don't know.
I have one quick question. So you showed some of these avalanches from energy estimates.
Yeah.
Is there some sort of specific events, spatially varying events, like you had a couple of images about the shear localized regions and so on, right?
You mean
in the first part. Yeah, this one, yes.
Yeah.
So when you have something that's dense versus loosely packed,
yeah.
How does, like, let's say for some particular loading condition, just tracking back on the previous question a bit, if you see, let's say, bunch of bands versus more diffuse deformations, is there something you can say about some of these statistics from that?
So the point is that they seem to be statistically equivalent, right? And we can look at the game. Look, I have here a movie. So this is just the fastest avalanche that is moving. So this is what I'm representing with these blue dots, right? The fastest and second fastest avalanche bits that are moving during one avalanche, right? And this is a loose assembly. You see that they move. I mean, they can happen everywhere. So a single avalanche can have particles moving all around, right? And you'll think that something much different will happen in loose assemblies, in dense assemblies, and it does if you are on this soft particle limit. But on stiff particle, I mean, of course, if they are localized in the shear band, and they are a little bit more focused. But sometimes you have an avalanche that also propagates very far away. So we are still in this situation where, of course, the activity has been focused, but it looks like it's not that. It's not that important, I mean, on the statistics. What may happen is what happens outside of these bands, right? Probably, I mean, this is something that I'm not an expert, but probably this the assembly is still over-compactified there, right? And here we are on the band, we are in the situation where they can sleep, where they can establish this stability limit, right? That is very similar to the one in the loose assembly, right? I guess this is what is happening, but I have no proof of that. Yeah.
And just a thought about, linking back to some of the results we saw in yesterday's talk. If you cycle it, with a certain amplitude and then do a training type readout type of thing, do you expect intuitively different statistics?
I guess, sure. Because especially those what you have, here you have this training. I mean, in loose assemblies, I don't know sure, but in dense assemblies for certain. Right, because you have this localization process. Let's say that the formation of the localization band has to do with this over stiffness, right? With this weakening regime, let's say that we observe. Yeah. So this is definitely like passive deformation, and then if you go back, you'll have some memory on that, right? Certain.
All right. Any other follow-up questions? Okay, if not, then let's thank our speaker again. And thank you very much to all of our speakers today in the morning session. We'll break for lunch, 1 p.m. Thank you so much.
This
Okay, so one quick announcement. So the bus towards Mahabali